You're writing a new application, which means you have 0 users. So do you really need a distributed cache or a dedicated system for full text search? Stick around and I'll make the argument that the only thing your application needs is Postgres. I'll show you the features of Postgres that will simplify your application and how far you can push it before things start breaking down. And I'll show you actual examples of real-world numbers of how much your database can scale. It's probably a lot more than you thought. If you're trying to ship a product, then you don't want to complicate it by having a whole suite of services that it relies on. That'll just slow you down, especially if you already have a database that will meet all your needs. It's easy to fall into the trap of adding tech just for the sake of adding tech. I know I have to guard against it myself. Sometimes it's because as developers, we love working on new tech every day and learning about new tech every day. So we want to add all the shiny new toys to our application. But when you're trying to ship fast, your mindset has to change. If your goal is to get a product out quickly, then you have to have the discipline to rule out unneeded complexity. You might also try to justify it by telling yourself, well, I might need it eventually, so why not just save time and add it now? The problem here is that you might not eventually need it, or it might be years before you actually do need it. But the trade-off here is that you're going to be taking more time writing your application, which means you're going to be releasing it later in the future. So you're spending more time writing the application, and then you're also going to be spending more time maintaining the extra service and all the extra code to integrate with the service. The common cost here is your time. And as an indie developer, as a solo developer, your time is your most valuable resource, your most scarce resource. So you should be ruthless about avoiding any waste of your time. So what if you actually need something like Redis, MongoDB, or ElasticSearch? How can Postgres fill that need while your user count is still low? Let's dive into that. First, let's look at Redis. What if you think you need Redis for caching queries and responses? Well, first, if your queries you're going to be caching are to your database, the first thing you should look at is, can you optimize your actual database queries? Can you improve either your SQL or how you're storing the database? Maybe you can add indexes, partitioning. Maybe you can find that bottleneck in your SQL statements and make it more performant so you no longer need the caching and you can just talk straight to your database to get the queries. Learning how to optimize your SQL and data in Postgres will go a long way towards extending the scalability of your application. But what if you actually need a fast cache? Maybe you're making external calls to a slow API or something. Well, you can consider using Postgres unlogged tables instead of Redis. The main difference of an unlogged table in Postgres is that the unlogged tables disable the write ahead log that's used inside Postgres to protect against things like data integrity problems, and if the actual application crashes, it's going to be able to restore to a sane state. But for a cache, we don't care about that. If something like that did manage to happen, it doesn't matter to us if the cache is wiped out. We just need to go and refetch it. So in this case, unlogged tables are great for this use case. It won't be as fast as Redis, but you can still get hundreds of writes per second, which is going to scale pretty well for a while. Let's look at some tests against a version of Postgres running inside Docker on my local computer. So in this first test, we're going to update a table that has 1 million rows of test data. And you can see in the first test, which is to a regular logged table, it takes 3 seconds to update those 1 million rows. Now, if we switch over to an unlogged table, that same update for 1 million rows only takes 1.7 seconds. So that's almost about, 2 times speed up there. Pretty good. And then here in a second test using pgbench to run a bunch of transactions for 10 seconds and figure out what the throughput is, you can see that the log table only manages to handle about 1,000 transactions per second, whereas the unlogged table can handle almost 2,500 transactions per second. That's a 2.5 times speed up just by switching to unlogged tables. So when should you actually consider using Redis instead of Postgres? Well, if you truly do need sub-second response time from a cache, then you might need to use Redis. Or if you have some large-scale pub-sub type architecture that you just need to have in your application, then again, Postgres won't meet your needs, but Redis is a good fit for that. So what about MongoDB? Let's talk about that one next. The advantage that MongoDB has is that it's a document store, which means you can store schemaless data and perform searches on that data. Well, Postgres has built-in support for JSON column types. You can search within those JSON data, kind of like you would in a document store, and it even has a built-in indexing that can make those queries faster. The GIN index, which is GIN, that's a generic inverted index, is meant to be used with data that's supposed to be split up and then searched within the split up information. And that's perfect for JSON, where we want to be able to take a JSON object and then split it up into its key and values and be able to search across that. That makes searching the table for these values a lot faster because we don't have to do a full table scan. Instead, we can look inside the index to see what rows match. And you can even be more specific and tell the index to only care about certain keys if you know that you're only going to be searching for a particular key in the document. Just to show you a quick example of how this works, here we have a quick table I created that just has a primary key and then a JSON document. And I've created two different documents so we can have some test data. So you can see that built into Postgres, you have operators that allow you to search the documents by key and value pairs. But you can see here, we can create a GIN index on the JSON column, and that will make the queries significantly faster. Additionally, you can specify what key in the document you want to index, and that'll make it even better because you're not going to be wasting space in all the other document data, and it should be faster then. So when should you actually use Mongo instead of Postgres? Well, if you need to have high throughput writes on your document data, that's going to be a case for using Mongo instead of Postgres. The problem here is that the GIN indexes that we created, those are expensive to write. So if you're doing a lot of writes to your database, then those indexes are also going to take up a lot of time and it's going to slow down your transaction speed. So if you truly do need high throughput write speed, then maybe you do need MongoDB, but otherwise, Postgres could fill your needs. Last, let's talk about ElasticSearch. If you think you need ElasticSearch, then you're probably in need of some kind of full text search capabilities. Once again, Postgres has solutions for you. Out of the box, Postgres has the TS vector column type, which you can combine with generated columns and GIN indexes to really speed up your queries. The generated column is a feature in Postgres where you can have a column that gets automatically filled in based on other data in the row when you add or update that row. And in this case, it'll populate with TS vector data from the text you want to search. And the TS vector data it contains is a version of the data that's more optimized for searching within it. And then you can add a GIN index onto that TS vector generated column, and now your searches are even faster. Using TS vector will give you all kinds of ways to optimize your searches. In addition to the basic syntax, it'll also give you access to proximity searches, ranking, highlighting, and more. Just check the docs. But often you don't need all the features and complexity of TS vector. You can go with something that's easier and more effective, which is a common extension known as the trigram extension. In your database, that's PG_TRGM. This can dramatically improve your searches by storing trigrams, or groups of 3 letters that are inside your text, in an index that you're using for searching on a column. These new indexes can be used with like statements and I like statements to search through your tables. And if you read the docs, there are even more operators and functions that allow you to do more advanced searching and even scoring on your data. So here's an example from an actual table that I'm going to be using in production. This table, which is storing TV and movie data, has over 360,000 rows in it, and I want to be able to search on the titles. So you can see if I just do a simple I like statement without any optimizations, this query takes me over 6 seconds to return. That's obviously not acceptable. This is not going to be a production ready solution. So the first thing we'll do is I'll show you how the TS vector and GIN index combination will work. So this table already has a generated column for the TS vector data, and I'm going to add an index to that column. In this case, the column name is title_FTS. So you can see that I'm going to add this GIN index to it. And now when I run a TS vector type query against it, you can see it only takes 478 milliseconds. That's way better than 6 seconds and actually usable in production. But let me also show you the trigram solution. In this case, the trigram extensions are already enabled on this database. And now I'm going to add this trigram index to the actual title data. So not title FTS, but title. And when I run the query, you can see it returns in 415 milliseconds, which is even faster than the TS vector solution. This is the one I'm actually going to be using in my production application, but now you've seen an example of how these can work on a table that has, over 360,000 rows. So when do you actually need Elasticsearch? Well, if you actually do have a huge amount of text you need to search through, you're probably going to be better off using Elasticsearch just because of the capabilities it provides. Another possibility is that if you have complex requirements about how you want to return relevance about the queries, so being able to identify, how close the documents are to what was searched, then that might also require Elasticsearch. Those are the advanced features that Elastic provides that Postgres won't be able to. But if you're just doing basic full text search, then you have multiple options in Postgres that'll scale well with your application. Let's say you're starting to agree with me and you're thinking, maybe Postgres is all I need. How do I know if my database will handle my traffic? Well, that comes down to basic sizing of your database, which means you have to make some assumptions about your database traffic, your database size, and then do some math. For example, let's say you have a transaction that you're gonna be running all the time on your database. And let's say it takes 5 milliseconds to run one transaction on average. Well, if your database has 2 CPU cores, then that's going to be about 400 transactions per second that your database can handle. You can come to that just by taking 1, dividing it by the number of seconds it takes to run a transaction, so 0.005, and then multiplying by the number of cores. It's important to find out how long your transactions actually take. This way you can have a more accurate estimate of your capacity. Once you know this number, you have to ask yourself, how many users will I need to be using this before I have to worry about running into that capacity? In our case of about 400 transactions per second, let's assume that our users on average will be doing this transaction about once a minute. In that case, we could handle 24,000 active users, and that's just with this base level 2 CPU database. Well, then you have to worry about the RAM on your database. But again, assuming like a very small database, so 1 gigabyte, which is the smallest one you can get for the paid version of Supabase, a very quick back of the envelope math says, well, if you estimate that your rows are about 1 kilobyte in size and you have a gigabyte of memory, you can handle like tables that are about 1 million rows in size. It's not, that's kind of getting you in the right scale of it, but in reality, the memory is going to be partially used for the operating system and for the program itself of Postgres. And then Postgres does split things up into a buffer for caching and then the actual working memory. So you can still assume though, that you can easily handle tables that have hundreds of thousands of rows without any problems. And all this assumes that you're at a very low price point in your database. If you really do need to scale up initially, the first thing you can try doing is increasing the database that you're on, paying a little bit more for a bigger database. For example, looking at the Supabase pricing, an 8-core 32 gig instance costs $410 a month. If you're at the point where you need this database, you should have thousands of daily active users, which means hopefully $400 a month isn't that big of a deal. Otherwise, you have monetization problems. And with a database this size, you should be able to handle like 10,000 transactions a second. And if your data is well-formed and well-indexed, you can easily handle database tables that have 50 million plus rows. So how do you decide if you need an extra service when you're architecting your solution initially? If you aren't absolutely sure you need a service, then you should follow this one simple rule, and that is prove you need it. In other words, default to using Postgres, but then follow these steps to figure out if you actually need another service. So first, with data loaded into Postgres and you're actually running real transactions or queries, measure the performance of those and make sure that they're going to fit your capacity. You can use tools inside of Postgres like pgstat statements or explain to figure out where your bottlenecks are. If you find performance problems, step 2 is to optimize. Use explain. Try adding indexes, tune your query, try adding partitions. The goal here is to find ways to improve the performance of Postgres so it meets your capacity needs. Finally, if you run into a wall and you can't get over it using Postgres, then go ahead and use that new service. You've just proved that you need to use it. But remember, you're trying to prove this is a solution you need now. Is this solving a problem you actually have today? Or is this solving a problem you imagine you have? So remember, your Postgres instance is probably 10 times more capable than you're giving it credit for. Drop a comment if you have any other tips or tricks for Postgres that I didn't cover here. Thanks for watching, and I'll see you next time.